So how does CART fit into this? Where we see CART fitting into this, number one is in the cost modeling. CART doesn't do a very good job with continuous response variables like severity, claim severity, but we have had some success in using it to assist with our modeling efforts when we're modeling claim frequency. Also, two of the case studies that we're going to talk about today talk about retention and conversion modeling, which is just a binomial response model, accept reject type argument, and we've used CART with that as well. And certainly there, in the insurance industry, there are marketing and fraud detection opportunities that are classic tree applications. If I just talk about the strengths of the two software products, from CART's perspective, it easily rank orders variable importance. It's kind of a nice feature. GLMs don't necessarily do that, so it's a nice handy output that comes from CART. I say here automatic interaction detection. I don't know if I'd say it's automatic, but it requires work to kind of understand what you're seeing. But it does give you insights into where interactions may lie. It can capture multiple structures within a data set rather than a single dominant structure. So a GLM requires it requires an underlying assumption about that underlying distribution, and to the extent your data has sort of a multi-distributional data set, then you are going to have troubles, and you're going to have to find a way to split that in a GLM, but where CART would not have a problem with that. CART uses surrogates to handle missing values, so that's a really nice feature, and it identifies key splits in the data. So sometimes what you can find is that one of the examples we go over, you might find that sometimes splitting the data and actually building two separate models so you don't have a ton of interactions floating in your model might be a little easier to manage than to have one big model that just has lots and lots of interactions. And it works well for categorical response variables. Emblem, I think some of the things that I've already talked about here, it gives the user control over the model structure. You can create continuous curves among your predictor variables, which helps ensure meaningful relationships between levels of predictor variables. So if you have, for example, accident frequency for an age curve, and you're trying to identify, what's the claim frequency for a 16-year-old versus an 18-year-old, we can, in a GLM, we can ensure sort of a smooth decreasing curve or something, so that we know that 16-year-olds do have higher frequency than 17 and 18, and so forth. So we can keep those meaningful relationships between the levels of the predictive variable. The ease of communication and conceptualization. So the effects of each explanatory variable is transparent. You can kind of see it. You can see how it's what it's producing. It does well for developing a mapping for new data points, and can handle very large data sets. So what we saw from our side in the insurance industry as a use for CART was to use it to help identify the factors that we found to be predictive. So if we have what's happening in the insurance industry, as it's happening everywhere in the data industry, is that people are throwing more and more data at more and more levels of predictor variables to see whether or not they have any value in explaining that response variable. And as you start to increase the number of predictor variables, it can bog down a GLM as you start to manually process through all of these variables to find out which one is predictive. So CART kind of gives us a quick and easy way to identify which factors might be a good starting list from which we could use. The other thing that we have found handy with CART is that it can give you some insights into interaction detection. So if there is any interaction going on, you can look to CART to see what it tends to find. Model validation. Segmentation, again, segmentation is what I was talking about before, where you might decide that, for example, we did a homeowners insurance analysis, and it found that there was a certain split on the data right away that made it easier for us to build two separate models on that split rather than one combined model with a lot of interactions. And extrapolating unknowns, there was another project that we did with homeowners insurance where we wanted to pull in some information about the age of the homeowner. And the age of the homeowner is usually something you don't actually capture on a homeowner's insurance policy application. But you do capture it on the auto insurance application. And so if you go to your data set and find out the policies where you do have age, where you wrote both, the homeowners and the auto policy, we were able to basically populate our unknown data set and predict what we thought the age grouping would be for this unknown data set so that we could populate that and use that in our modeling. On the emblem side, with that information in CART, we still intend to build the model structure within emblem, and mostly just for the documentation and support side of it, the ability to still kind of control the process, and we're going to use it for the implementation of the results because the output of a GLM is exactly the structure that we're looking for anyway when we're actually developing rates for an insurance company. And the other thing that's handy with Emblem is that it will incorporate the time and seasonality trend effects of your data without having to actually build that into your results. So you can have 3 years of or 5 years of claims severity data, whereas naturally inflation is going to be a factor over that time horizon when you're analyzing all that data combined. You can put into your model a time variable so that it pulls in that inflationary effect, but then not use that and kind of normalize your data set when you're actually developing relativities and rates for your future policyholders. So before I get into the case studies, the one thing that I do want to point out is that this is not a question of which is better and which one should be used. This is an exercise of seeing how we can use both and get more value from just using one. And the purpose of this discussion, as I say here, is to show how efficiencies can be gained in the modeling process, especially as the data sets get larger in terms of the number of predictors. Time can sometimes be a crucial element. Just with anything in business, companies want results quick. And so sometimes the faster you can get a result, even if it might not be optimal, is better than saying, hey, we need 9 months to get our work done. Not that it would take 9 months, but certainly the entire process, sometimes for an insurance company, to develop a new rating algorithm might actually take 9 months or a year when you incorporate all the steps, the regulatory approval, the management buy-in, getting the underwriters who actually write the policies to get it set up, to code it in the system and everything else. It's a long, lengthy process for every change. So why don't I start with the first case study. The first case study was a U.S. retention data set. So this policyholder retention, the response variable is just yes or no. And, did the policyholder renew is basically the question. The data set had 97,000 observations, where each observation represented one policyholder that was either renewing or not renewing. And we split the data randomly 50-50 between training and test. And there were only 11 predictor variables in the data set, so a very small data set, total number of levels, 147. And what we did is we took the data, and Mikhail and I kind of took the same data and said, okay, let's just run some stuff and see what happens when we throw it through CART, and let's throw it through Emblem and see what we can do. For Emblem, what we did is in a GLM, if you want to automate the process, I mentioned it is a manual process, but you can automate it by using forward entry regression. I'll talk about that in a minute. And we did that using the chi-square statistic. I guess I can talk about that now and just skip forward and come back. What forward entry regression is basically you start with a mean model where you just had the base parameter in there. You could actually start with anything. You don't have to necessarily start with just the basic model. And you specify whatever criteria you want for improving the model fit. And in this case, we chose the chi-square test and told it basically to use a threshold of 5%. And so what it did is it ran through a series of iterations where it built various different models. Model number one, well, the very first model it built was just the mean model. Then what it does is it builds another model, the model number 1, which was mean plus gender, and calculates the chi-square statistic, and so forth, and cycles through all the variables. It then finds the variable that has the lowest chi-square statistic, and chooses that as its new starting point for the model. And at that point, then you iterate through the remaining variables to see where mean plus policyholder plus whatever is the next model to build. And you continue doing that until, in this case, the addition of no other variable produces a chi-square less than 5%. At that point, the iteration stops, and you have an initial model.